Okay, let's begin. It's 9:30 and we've got a packed agenda, please. So let's get started. Hi, everybody. As usual, we're going to start with the note wall. So I'm going to just quietly go through the note wall slides so that you all can take them in.
And as a reminder, while Wojtek has that slide up, that's Wojtek Kozlowski, who's one of the co-chairs, and I'm Rod Van Meter, the other, joining you remotely.
And to wrap up the note wall, just a reminder that the IETF is for research, not for standards development. So we're here to foster research collaborations.
Wojtek, the back up for just a second to the ombudsman slide. We should update this slide also to mention RFC 9775, which is the IRTF Code of Conduct, which was published not too long ago.
Good reminder for next time.
Yep.
Session is being recorded. Those of you who are in person, please scan the QR code to appear as a participant and raise your hand if you want to ask a question. Remote participants, I'm sure you can figure it out. All the buttons are on the IETF agenda website. So let's start. So today we have the 2 hours for the QIRG meeting at the IETF 123. I'm Wojtek, I'm one of the co-chairs, and Rodney is online, the other co-chair. Say hi, Rod.
Hi.
Yeah, and usually Rod is online this time. Usually he's here in person. But okay. Agenda. Today we have a very packed agenda, so I'm going to be very strict with chairing. Please, all speakers, respect your time. It's 20 minutes for each talk and 15 minutes for the draft update. And I appreciate it's nice to finish a question, but I will aim to finish everybody at their time in order to make sure that all the follow-up speakers have time for their session, because we're running up exactly up to 120 minutes with it as shown. With that said, just one last thing. There's actually a document in progress on which there will be an update at the very end of the session. There's been an update early July, so it'd be good to discuss it at the end and after the session as well. Rod, do you have anything else to say before I hand over to the first speaker?
Not a thing. Let's go.
Great. Okay. Amar, can you come online and share your slides? Okay, right, great. Amar, you have 20 minutes. I'll stop you on the clock, including Q&A.
Okay, thank you. Hello, everyone. I am Amar Ben. I'm a research engineer at NIST. Thank you for the opportunity to share some of our current work regarding network abstractions and evaluation for quantum networks. Okay, so our current work that I will be covering today is essentially continuation of our recent survey we published on routing entanglement in quantum networks. So we reviewed the literature for fixed optical quantum networks and also for bipartite entanglement distribution. So just a quick summary, of the taxonomy we proposed for the different approaches and networking paradigms for these routing solutions that will be necessary for the upcoming slides. So we essentially separated the routing and the forwarding phase, and in the routing we also have two main approaches: the proactive and the reactive. So quickly, the proactive is when the path computation and installation is done before the entanglements, the elementary entanglements are generated. And the reactive is when it's the path computation is done after the entanglements are generated on an instant topology of the entangled network. And then these two, we can call them paradigms or classes, can be designed and implemented either distributed or a centralized environment. And then comes the forwarding phase, where we have essentially the purification and the swapping, which are the operations necessary to establish the end-to-end entanglement. And here we are specifically interested in the purification with a purification scheme, which is dynamic and provided to the nodes at runtime, which tells, for example, which link or segment needs to be purified and how many links, how many rounds are needed. And then, of course, there is the main operation that makes the quantum networks so special, or one of the main ones, which is the swapping. And in the swapping, we also have either predefined static or arbitrary orders, like sequential or doubling, or we can have not an order but a policy, which is some rules that informs how the swapping should be coordinated. And the simplest one, for example, can be the swap as soon as possible. So it's not an order, but it's a policy. And then we can have heuristics or other optimization approaches for more dynamic and more adaptive cases, which can be per path optimization, for example. So beside this taxonomy, we also provided some remarks on network abstractions, which is the main topic here. So yeah, we think it's kind of too early for a protocol stack standardization, and also because it's very related for also the control and data plane. So we all have in mind the generic protocol stack we used to consider as like the entanglement, the link layer for entanglement generation, and then the network layer for the routing and forwarding phases. But more than that, it may be too early. However, if we view the problem as from the network function and services perspective, this shows from the reviewed studies shows more convergence. We used to like to see the same or very similar modules or components that are considered in repeaters, for example, or in at the network level. This will also inform on the protocol stack and more advanced organization or standardization. So we are taking this perspective in our work. Another way to also look at this, there is so in the topic there is abstraction and there is also evaluation. So in terms of evaluation, for the studies that we rely on or we collected for the taxonomy, we calculated that large portion of them either use custom simulators for evaluation, which may be like missing of the in terms of flexibility or comprehensiveness of the some of the available tools. Because if you are to develop your small simulator, you are probably okay with some programming, but if it's too difficult, then it's probably people just go with their custom small simulator for their specific cases. The other also important part is the studies that rely on analytical models. So this is more for a quick evaluation of the idea or the protocol without the other like considering the other aspects of programming within the simulator. But we also have a large number of available simulators which we use also in our different evaluations. So I have this nice trend from ChatGPT. So it has to. So you need to take it carefully, but it just shows the trends on the simulator usage on a broader set of studies, not the ones we reviewed especially. And we see the early simulators that responded to early questions or early needs of in terms of research. And then as new simulators come, they of course try to answer the current or the next challenges in terms of research. And what we see in our work as a need for now is the need for direct comparison of these paradigms we identified or we may identify in the future. As an example, I mentioned the proactive versus reactive approaches, but also the interaction of these different processes and functions within repeaters. So we want to have more comprehensiveness in this evaluation. So if we want to evaluate multiplexing, for example, we want to also to evaluate how it interacts with swapping strategy or swapping policy, and also with a purification scheme, and these kind of interactions. And so not just evaluating one aspect in isolation. Yeah, of course. If it's quick, it's always interesting especially for prototyping. And yeah, there is also the try to bridge a gap between the physical architectures we see that are the sort of the only implementations or the only realizations of quantum concepts, and how to bridge them into a more like higher level routing and protocol design, where we view all this problem really as networking problem. So we're designing a tool for to answer these two aspects of abstractions and evaluation. So we can view it more as a prototyping tool for quantum networks. So the idea is not to have like much physical details or details from the quantum physics, but we want a faster and more comprehensive tool that can be used for evaluation. And as I said, the inter-paradigm comparison is, I think, is interesting to have now. And our approach also is we don't want to come up with a perfect architecture to start with, but we start with a very minimal structure just for code organization, and then we refine it iteratively as we add more of the functionalities you see on the right hand side of the slide. We also try to keep one aspect, that's to keep the design of the tool realistic. So we want to design it as something that can be also an emulation of 1G quantum networks. So we don't, for example, we try to avoid components that don't translate into physical or a software element in real quantum networks. That's what we have in a lot of simulators, like a resource manager for the global network, for example. These things usually don't map directly to some components in the actual network. And there is also another aspect of that's very useful in classical networks, which is network analysis and verification for routing, for example. And can also be interesting to see how this, what this would be in terms of quantum networks, beside the physical aspect, but in terms of routing and the protocol aspect. So for the functionalities, we try to identify the functionalities that we relied on for the taxonomy. And of course, there is the heterogeneity of the link architectures and the channel capacities. I mentioned the purification scheme, configurable at runtime. And same thing for swapping, and also everything related to multi-tenancy and the multiplexing. And of course, I already covered the proactive, reactive, and distributed centralized environments. So now I'll just quickly cover three main components we are developing or we're integrating into this tool. So the first one is in the continuation of the survey, we try to review and organize the different cases of memory management or resource management. So there are resources related to the channel, to the quantum channel, which are essentially the qubits, which can be assigned either in a static way for a topology creation, either in symmetric, so same number of qubits on each side, or there may be cases where the asymmetric can be interesting, for example, in the sender-receiver link architecture. But we are also looking at what I highlighted in blue. It's the dynamic qubit assignment, or it's you can think of it as a virtual memory we have in operating systems. So the idea is to try to support higher number of channels with a lower number of qubits by assigning the attempts. So when we do an attempt for an entanglement, we do it for one channel, on one channel, and we may do it for the same qubit on a different channel. And we use models also for finding heuristics and policies for this. And the other aspect for regarding the path is the so we know the static allocation and the dynamic, which translates into the statistical multiplexing and the buffer space or blocking multiplexing. But we are looking also at dynamic allocation of entanglements when they arrive. So it's not related to which other entanglement is available for swapping, but it's an allocation based on the needs of the path and different parameters that can be also considered for this. So we're looking into this, but also supporting the other strategies that are already there.
Hi, Amar. Just want to point out you have about 4 minutes and 20 seconds and you're on page 6.
Yeah. Yeah, the next one is the qubit management. Again, to support the inter-paradigm comparison and the dynamic configuration, we are also integrating sort of unified life cycle for the qubit. So this one is inspired from work published a few years ago, and we are working on extending it to support the different all the different features I mentioned before. So I'll just go quickly to the next one. Next one is also important in terms of heterogeneity and integrating the physical properties or the physical characteristics of the quantum network. So we know that there is no single qubit platform that supports or that provides all the necessary features for quantum networks, depending on the application, on the scale of the network. So we are also reviewing, we are working on review and framework for the different link architectures applied to different qubit platforms, essentially the ones with photonic interface and the ones with microwave interface that need transduction. And also the case of transduction within the photonic interface, and then the different encodings that can be used or that are the most popular ones. So this also is integrated into the simulator or the tool for network prototyping. So now to finish, we are so how all these elements are put together. We are working on an initial architecture to start with to demonstrate all the interactions of these aspects. So we started with a proactive centralized, which is probably the most used one, and we start identifying some components which we will refine as we add more features. So the idea here is to identify when we go to another type of paradigm, identify where the differences are and just keep maintaining the architecture for this. So we try to keep the architecture evolving as we add more features. So I think so here we have just a few examples of networks and small networks we are working with, but I think it's fine. So I'll just stop here for the presentation. Thank you.
Thank you, Amar. Time for only one quick question. So whoever raises their hand first gets to ask. Go ahead, Diego.
It's going to be very short. It's about simply about this that you are thinking you're going to make an implementation of this. Do you plan to make an implementation of this, make it available as open source or whatever, or just working on the architecture? Just out of your concrete plans on this?
Yeah, we have actually, I forgot to mention it, we have an implementation of this which will be shared very soon. So this architecture is implemented that you see here with different features, multiplexing, swapping, and purification. Yeah, so we plan to release it. Yeah.
Okay, thank you. Thank you, Amar. We'll move on to the next talk, which is design and development of quantum network simulation and module for NS3. I'll let the speakers introduce themselves.
All right, hello everyone. I'm Mohit. I'm from the National Institute of Technology, Karnataka, Surathkal in India. And I have a team of students, and together we have worked on the project which is called Design and Development of a Quantum Network Simulation Module for NS3. NS3 is a very popularly used open source simulator. A lot of work at IETF happens using NS3. So we have a funded project from one of the organizations in India, and we pitched in, and they have supported us with this. I'm having a big team of students. Could not bring all of them, but we have about 5 of them, and I'll hand it over to them to take this presentation forward.
Yeah. So quantum computing is there's rapid advancements in today's days. So um, there's an increased interest in developing quantum networks, but quantum networks are needed to like connect the quantum devices and enable communication. But they're limited um, by the high cost of this, and they are also in yeah
You can see that. Yeah.
yeah sorry, they're limited in availability, and they're like geographically isolated at times. So we decided to use a quantum simulator. So why do we need a quantum simulator? Quantum networks, so simulators can enable rapid prototyping and help us and test the hybrid quantum classical protocols. So we decided to build upon NS3 and create a quantum module for that because of NS3's strong support and a large user base and maintenance. So we are building a module that can integrate the quantum and classical networks together, and we are providing the flexibility to integrate, prototype, and benchmark different quantum simulation backends with NS3.
Yep. So continuing with the motivation, one of the main requirements of any quantum network simulator is basically to provide all the capabilities of mature quantum simulators like Qiskit, etc. For our module. So hence our purpose over here is not to create a whole quantum simulator itself, but to extend the support to include various other mature quantum simulating tools such as Quantum++, which is currently being used in the version 1.0 of our release. And to facilitate the support for such quantum tools, we basically have a class called the Quantum Helper, which acts as the interface between our simulation module and the quantum backend that can be used. So over here it's Quantum++, but later on we can also add other simulation modules such as uh, Qiskit, AER, etc. So the quantum helper basically has all the definitions and implementations for all the basic quantum capabilities. Now over here it includes formalisms such as state vectors, density matrices, and also basic operations like quantum operations, gates, circuits, etc. Now, along with the quantum helper, another main entity within our simulator is the quantum manager. It basically acts as a central entity where all our representations and metadata regarding the simulation gets stored. So this includes the storage of all the formalisms. Now, since we have Quantum++, currently we support state vectors and density matrices where each of these representations are mapped to an ID to be used within the simulation classes. So for example, if we have like a qubit, the qubit will be generated with an ID, and to perform any other operations using the quantum helper, the representation from the quantum manager can be used, which will be mapped to this ID. Um, there are more components within this quantum manager. I'll come to that shortly. But now coming to the main quantum network simulation, we basically try to map it to real quantum networks and the design patterns used in NS3, which basically involves having something called a quantum node, which is the physical quantum entity for our simulator, which is basically responsible for all the hardware for entanglement generation, having the quantum memory for storing entangled qubits, and running all these circuits, which are basically done through the quantum control. Now, each of these physical entities, which are the quantum nodes, are connected using a point-to-point link like an optical cable called the quantum channel, through which qubits can be delivered from one node to another. And all of these physical abstractions inside the quantum node, we basically have like abstractions called the quantum devices. Now, each of the nodes can be aggregated with protocols and apps, and these quantum devices or these abstractions are the ones responsible for using such applications and protocols. This can include EPR pair distributions, purifications, etc. Uh, now, of course, quantum simulation is never complete without modeling noise. So we also support like noise models within our simulation as a separate class. And there are certain predefined noises like depolarization, phase shift, bit shift, dampening, etc. And all of these noise models can be mapped to each of these components, such as the quantum channel, the memory within the quantum nodes, the noise associated with each gate. And these are also stored as ID to noise model mapping within the quantum manager. So basically, this is our quantum architecture that we propose for this. And now how we are, this should basically enable not only, like this should enable us to emulate all kinds of components within a quantum network, including repeaters and routers with the combination of apps, protocols, devices, and nodes. Yeah, so now how we are going to integrate this quantum network architecture within our simulation module to NS3's classical stack for realistic hybrid quantum classical stack will now be explained by Anirudh.
Yeah. So building upon that architecture, like let's look into how we have integrated the architecture into the NS3's ecosystem. So our code design principle was to reuse and extend NS3's existing capabilities and not reinvent the classical communication and the like simulation stacks. Uh, and we have also integrated third-party libraries such as Quantum++ and Crypto++, like using NS3's CMake build system. Crypto++ is mainly required for cryptographic application purposes, which will be covered shortly. But Quantum++, on the other hand, it's also interface with a quantum helper interface, so which essentially provides the like functions to like generate and measure qubits and much more. Essentially, bringing all the quantum simulation capabilities into our module. Uh, the NS3's classical stack has been like used to model our quantum network stack as well. So the classical stack is made up of nodes, the physical entities, the net devices, which are the network interfaces like present on a node. Then we have channels for like setting up a point-to-point links, and then we have applications like which basically like runs certain programs over a configured network. So drawing the parallels, we have quantum nodes, we have quantum devices, quantum channels, and quantum applications or protocols. The quantum node, it has access to the quantum resources allocated to it by through an aggregation to the quantum control class, like which essentially provides all the simulation and monitoring purposes for all the resources which have been assigned to a node. The quantum resources have been modeled using quantum circuits, gates, registers, and quantum memory, each of which also have their own physical characteristics such as noise and decoherency effects. Uh, Moving on, we have quantum applications which are just like a regular NS3 application, but also access to quantum like resources allocated to a node. So this essentially like like enables us to perform LOCC, which is like local operations and classical communication, like while also staying true to the network like scenarios such as congestions and all. Then we have quantum protocols. These are required to like model protocols for distribution of EPR pairs and purification and so on. These are just like regular NS3 objects, but these can be aggregated into a quantum node like using the NS3's object system. And finally, we have the quantum channel, which enables the qubit transmission between multiple nodes. So right now, like we can also
configure the channels with their own delays and noise models as well. So right now we are like using point-to-point links like from an S3, which implies that we can only run, like certain kind of application on a particular node, because it only communicates between two devices across nodes. But like we are planning to extend the capabilities of like such a channel to also like support multiplexing between multiple devices on the same node. So like we'll be also able to simulate much more complex quantum network components such as repeaters. Yeah, so that is all with the integration with NS3. Now my friend is going to explain from a high level, how this like simulation model can be used to perform like simulations like using applications.
Yeah, so as that explained about the architecture proposed and how it's integrated with NS3, all of that is within the low level. For someone who just wants to use the module to validate uh, some quantum protocol they're developing, or some application, some quantum application they want to do, you're going to use something called quantum applications. The name can be slightly misleading. A quantum application is anything that can be used to simulate traffic within the simulator and need not just stick to the application layer protocols that it could be misunderstood to. So one of the main purposes of this, it can be used to build prototype applications such as something that uses quantum classical hybrid apps for key distributions and other things. One of the main purposes of building such an application could be to validate the quantum internet architecture that we have proposed, or something you're building upon that. So let's say you build a repeater or something like that. You can just use an application that can simulate traffic to test this out. So you can also use this to do performance analysis, such as evaluating latencies, reliability under network conditions, what's your loss, how much noise you're facing over a particular distance, etc. You can, an additional thing we have also introduced is to enable testing protocols resilience to eavesdropping scenarios. This is from a security perspective that the quantum internet aims to this thing. So an example of an application we built within our simulator is the QKD application. So we built this inspired by the ETSI AGS QKD 004 standard. Keeping the modularity in mind, we separated key generation, storage, and application facilities. So this validates the quantum classic hybrid key exchange by combining quantum key generation, for which we use the B92 protocol, with classic cryptographic protocol uh, that we used AES 128 in order to send messages across multiple nodes. So for this, we also implemented event-based key distribution, where we generated key on demand. So an application can ask a key manager application for the key, and only then is the key generated. And other idea we are coming up with is a proactive key generation, where we have a buffer of keys, so that we can compare and benchmark the performance between those two. So we validated this after integrating third-party libraries, Crypto++ for SHA-256 hashing, and we built our own B92 application, which helped with error correction and privacy amplification. So coming next on to the challenges, which will be taken by Akash.
Yeah, sure. So I'll just quickly go about the challenges that we faced. So since the standards for quantum internet are still in progress, we had to keep in mind flexibility to accommodate further changes. There's also a trade-off between scalability and faithful simulation, which we had to take care of. And reliable entanglement generation in routing is complicated due to the probabilistic nature. And we also faced a couple of challenges integrating third-party quantum libraries with the existing NS3 CMEC build system.
Quick update about the project. So this module is now available on the NS3 App Store. And if you want to try it out, you can download it from the App Store. There is an installation manual as well. Here is the link to the App Store. We also have the code repository link here. So it would be great if we can get any feedback on the code or any contributions. Uh, Moving on to the development roadmap. So far what we have implemented is, so we started out with implementing physical level quantum abstractions, that is done. And then we also added support for LOCC with circuits and registers. We have added noise modeling of quantum operators as well. A few things that are currently going on are in progress, includes reliable entanglement for protocols, long distance communication with repeaters, quantum routing of qubits. Then there are a few things that we want to add in future. So right now we have added a use case of QKD applications for the validation of this architecture. Does this architecture even work? So we are able to perform QKD on top of this, but in future we want to add more applications to it. Also, right now in QKD, we have added support for B92 protocol, but we wish to add support for more protocols such as E91 or BB84. Thank you.
Yeah, I would like to thank QIRG for giving us this presentation slot, and to the agency that has funded us with this project. Thank you.
Right. We have 3 minutes for questions. Please raise your hand digitally if you would like to ask a question. In that case, I will start. To my knowledge, and Rodney can nod or not if it agrees, QISP or QUISP as you pronounce is also based on NS3. Are you able to explain the differences between your NS3 simulator and QISP? QISP.
Yeah. So if I'm not wrong, QISP is based on Omnet++, which is also a discrete event simulator, but not exactly as NS3. And Omnet++ is a general discrete event simulator, but there is a derivatory product of it called as INET, which mostly supports all the classical communication things. So if you had to use QISP, you won't be able to exactly use all the classical communication capabilities inside INET because it's another product. But if you go with the simulation module we have built for NS3, you also have access to all the classical communication stack which is already existing in the module.
Oh, that's actually pretty neat. Thanks.
Thank you.
Rodney, you're next.
He's correct. The QUISP is built on Omnet++, which is a system with some pretty substantial drawbacks we discovered after implementing it. That's an entirely different discussion. I wanted to ask actually a separate question. How do you go about verifying the accuracy of your simulator against physical experiments?
So at this stage, as I said, the purpose is not to exactly build our own quantum simulator, but have support for existing mature quantum simulations. So we have not currently reached that state, I guess, but we plan to integrate more mature quantum simulators so that we can ensure that at least the quantum simulation part is most probably reliable. So in our future, I think we are currently extending support for Qiskit AER. That's what we are working on right now as well.
Okay.
Yeah, I would just like to add one more point. For the classical communication models that we have in NS3, we typically use Linux network namespaces, and in the past we have validated a lot of models in NS3 with Linux network namespaces. But due to the lack of also available hardware with us and other complexities involved, currently, like one of my students mentioned, we have kept this thing to be done in the future. We haven't really pushed ourselves in that direction yet. But yeah. Thank you.
Thanks, Rod. Mahasaj, I see you're in the queue, but the time is actually unfortunately up. Can I ask you to ask your question online, and I'll let the speakers answer your question online? Okay, thanks. Let's move on to the next speaker, who is online, and it's Angela Sara. I'll let. Just a second. Yes. Okay, the floor is yours.
Okay, thank you, and good morning, everyone. I'm Angela Sara Cacciapoti. I'm one of the co-founders of the Quantum Internet Research Group here in Naples. So today, this presentation is around a topic that we are developing within my group. We are tackling this argument from a theoretical point of view to understand the role played by quantum transduction in the design of a quantum network. So I think I prepared too much slides, so I will skip some of them. So let's go into more details. We are very aware about the fact that the quantum internet in its final stage will be a global network, but recently there is a very high hype about quantum data center because they can deploy it in a more controlled environment. But despite the scale of the network we are selecting, what is important to highlight is that the heterogeneity will not come just with the vision of having this global network, but the heterogeneity comes within each node. And the reason is because currently there is no single qubit platform that can fulfill all the requirements that we have in terms of storage, processing, and communication. So this calls for quantum transduction, which is a functional, let's say, black box that should be able to convert one type of qubit into another by preserving coherence. It's so much important that also McKinsey, for example, in his last report listed the quantum transduction as one of the key elements in a quantum network together with the quantum repeaters, communications channels, and so on. So which is the problem here? The problem here is that some qubit platforms make transduction harder than others. For example, superconducting qubits that are considered very mature, a very mature technology for implementing fast quantum gate with high fidelity, operate at a microwave frequency, so in the order of a few gigahertz. But the community instead is very concord to say that for entanglement distribution, for transmitting a qubit, we have to rely on photonic technology. So when we deal with the so-called flying qubits, we are instead operating at optical frequency, so hundreds of terahertz. This means that flying qubits, optical photons, cannot directly interface with the superconducting qubits. So in this case, a quantum transduction is very needed. So you can think, okay, let's use cryogenic interconnections for avoiding the need of quantum transduction, since quantum processor implemented in superconducting technology can be interconnected by using these cryogenic cables, so all works at a microwave frequency. The problem is that by using a cryogenic interconnection, first, they are very, 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 very expensive, but also the installation is very complex, and you can achieve very short communication range. And another drawback is the fact that you cannot reconfigure the network topology, so the scalability is very poor. So at a certain point, also in more controlled environment like quantum data center, you have to rely on fiber-based interconnection, not only for assuring a long-range communication, but also for supporting reconfiguration of the topology. In particular, with the fiber-based, you can also think to interplay classical and quantum traffic, which is a very important topic for somehow letting the coexistence, the future coexistence about these two type of traffic nature. Okay, so with optical fiber interconnection, this transduction is required. And so we were interested in trying to understand the role played by the quantum transduction in the design of the quantum network. So we started by understanding that actually you have two, by using the same hardware, you have two possible functionality of this quantum transducer. You can directly transduce a qubit. This qubit can be an informational qubit or an bits, so an entangled qubits. And the transduction can happen in both the directions. So in the up conversion, meaning that you are trying to convert an optical, a microwave qubits in an optical qubits, in an optical photon, by preserving, of course, coherence. The down conversion is the opposite functionality. But actually, we also, and on this I will come back later, we also realized that with the same hardware, we can also exploit the quantum transduction to directly generate hybrid entanglement directly between microwave and optical domain. But let's start from the most intuitive functionality, which is this direct conversion. So the transducer is regulated by the hardware that is made. And in particular, for our purpose, for being able to somehow abstracting from the particulars of the hardware, we try to condensate the performance of a transducer in a parameter, in a called this parameter here called efficiency. This efficiency somehow is a probability that indicate if the transduction is successful or not. So you would like to have this parameter closer as much as possible to 1. The problem is that this efficiency is related to another hardware parameter called cooperativity, and I will explain why this is, in this moment, for the maturity of the technology, a problem. So, like I said before, you can adopt, you can perform this direct quantum transduction directly on your informational qubit. But here, which is the problem? The problem is that an ideal setup of the quantum transducer, you couple also the channel transmission losses. And due to the constraint imposed by the no-cloning theorem and the quantum measurement postulate, you cannot adopt, in this case, if the transduction or the channel, the physical channel, introduce impairments, the technique that we are used to implement in classical network. In particular, we try to let this concept to come out also theoretically. And what you can see here is that the success probability to have this transmission, as you can see, is a function of the cooperativity. So the efficiency at both the source and the destination. And for having a non-null quantum capacity, you have to impose a strict condition on the hardware parameter regulating the performance of the quantum transduction, since the up and down efficiency at the source and the destination should satisfy this relationship, which means cooperativity value greater than 0.3. And this is beyond the state of the art because this is the range of the cooperativity. So we have, in the best case, 10 to -3. So we are very far from being able to satisfy this constraint. So if instead of transducing an informational qubit, we focus on transducing an EBITS, and once this EBITS is distributed, then you can perform teleporting, for example, for sharing your quantum information, you can relax this condition for having non-null quantum capacity. And the reason is because entanglement is not information, entanglement is a communication resource. So you can regenerate the entangled states if the transduction, for example, fail. And this relaxation on the condition you can see here from this figure. In particular, this represents the subsequent teleportation process after the successful distribution of the EBIT. So here you can see that for having a non-null quantum capacity, you can rely on any value of the efficiency so that this can be more near to the state of the art of the technology. So at this point, the question is, can we do better with respect to transducing directly an EBIT? Okay, here there is another picture showing the probability of IPR distribution also as a function of the fiber length. So we consider the other functionality that you can implement with the same hardware of this quantum transducer that we call the entanglement generator generation transduction. So with this name, we wanted to capture the fact that with this same hardware, you can be able to generate hybrid entanglement directly between these two different frequency domains, so microwave and optical domain. But what are the performance of this entanglement generation transducer? Well, that depends on the way in which you couple, in which you design the architecture. And this is a very important point for stressing the role played by this transduction in the design of the network. So let me give you very few details that with this entanglement generation transduction, you can generate a two-level Fox states, and according to the pump, and if you initialize with some microwave signal, you can exploit a different interaction within the cavity so that you can obtain this state or this state, where this state, for example, should be read by saying that there is 0 photon at microwave and 0 photon at the optical domain. Instead, these should be read like there is 1 photon at microwave and 1 photon at the optical domain, and vice versa. So as I was mentioning, the performance of the AGT, it depends on the architecture. So if you couple, for example, AGT at the source and instead you exploit direct quantum transduction at the destination. So you are considering at the source generation schema that for distribution probability, you have relaxed the constraint on the cooperativity, but you are still need of a hard constraint on the cooperativity at the destination. But still,
just a small reminder, you have 4 minutes left including Q&A.
Yes. Okay. Thank you. And this is another vision from of the same results. So, what if instead we try to exploit this AGT without requiring direct transduction? So, in an archetype like this one, so we move from source point generation to both point entanglement generation with an optical repeater in the middle. This overall setup gives the possibility to determine the so-called quantum path entanglement. And in terms of performance, as you can see now, you can relax both the cooperativity at the source and the destination for having a non-null quantum capacity. But which is the price here? The price here is that the probability, the distribution probability does not exceed 0.5, and the reason is related to the hardware that you are implementing. So this is just a summary of the things that I try to describe. And for concluding, what is important to highlight is that we need to take into account the quantum transduction in the design of the network, since from these very preliminary studies, you can see that it affects the performance of the network, and in particular, the way in which you interplay the different functionality, the different nodes determine different performance of the network, and that's it. So thank you.
Right, thank you. Time for questions. Please raise your hand digitally. Mohammed Sajjad, please go ahead. We don't hear you, Mohammed. Any other questions whilst we wait for mic issues to be resolved? Go ahead, Rodney, for now.
Hi, Angela. It was a great talk. I didn't realize you guys are actually working on transducer stuff. Important work. Are you actually working with experimentalists on this? What's their reaction to the network architectural issues that it raises?
Okay, yes, we attacked the problem from a theoretical point of view, but because we also try to understand the state of the art of actual transducer implemented hardware, and the range is what I mentioned before. Now there is some of our PhD that are in a lab in US that are somehow trying to get confidence with the implementation, let's say. But I also skipped a part in the presentation because I prepared too much slide. Since we are also building this testbed for the quantum internet based on a source of entangled photons that works at telecom operator, so 1550 nanometers. The long term is to use these experimental results for somehow getting a better also channel model that we used for these theoretical results, we used just an airsure channel because there is nothing available. So we can also improve. And the problem is that...
Okay, can I stop the question? We're out of time and we really need to move on to
sorry.
the next speaker, sorry.
Okay, thank you.
Mohammed, did you fix your microphone? No. Okay, thank you very much, Sarah. Sorry to have cut you off, but we really need to be strict with time today. Can I ask the next speaker to come up, please? Thank you again. Just a second, it won't work yet. Okay, it should work now. Go ahead.
Hello, everyone. My name is Blanca. I'm a PhD student at IMDEA Networks and La Universidad Carlos III de Madrid. And today I'm going to be presenting to you this guy right here that is named Qudito. So what Qudito is today is a platform, an open source platform that allows you to emulate QKD network deployments. So what this means is that you can transform Python-capable devices to a commercial QKD node that interact with you following a standardized key delivery API. So why we built Qudito in the first place is because current commercial QKD hardware, first of all, is a bit expensive. So if you're trying to build large networks, you have a big cost there. And second, because they follow the plug and play principle. So it's really easy to use them just in a point-to-point kind of deployment. But as they are black boxes, most of the software and the hardware on those things are proprietary. So you cannot actually touch them a lot or do things with that. So what we did is we wanted to experiment with QKD network deployments and touch the protocols inside those nodes and how they talk and so on. So we needed something that allowed us to do that. So we built Qudito. And the way we designed it was as user-friendly as possible so everyone could use it. So basically what we designed to be the functioning are only 3 steps. So the user describe the network deployment they want to build, and then give that description to the Qudito orchestrator, and that's all you have to do. The orchestrator then connect to the physical infrastructure that may be Raspberry Pis, containers, virtual machines, whatever, and configure them to be to resemble a QKD node. So you can then interact with them as you would with real physical hardware. And how we simulate the quantum behaviors is with a backend. We call it simulator engine. And this design, it's really modular, so you can like change the simulation core. We give you some implementations of protocols, currently 2 different implementation of the BB84, but this you can change it wherever you like. So how we implement the design, we actually end up doing 3 different Python package, one for the Qudito orchestrator, one for the nodes, and one for the simulator engine. So we use Ansible for the tasks where the orchestrator have to configure the remote devices you have on your physical infrastructure. Then for the API, we choose ETCO 14 because it's one of the mainly used by commercial hardware. And also for the communication between the nodes and the simulator engine, we configure a RabbitMQ broker. And then, as I was saying, by default, we give you implementations of BB84 on NetSquid, but this is something the user can change if they want to use any other simulator. It's fine, just put that in there and it will work. And here, yeah. This is basically the flow you get when using Qdito. So what the user does is to install the Qdito orchestrator package and then start it with the description of the network. Things like name of the nodes, length of the links, protocol they use for key exchange. And then that's all it has to do. The orchestrator then start connecting to the different containers or whatever Python capable device and configure and installs the Qdito node package and the Qdito simulator package in one of those devices and set up the broker so the communication is possible. And then it starts all the required processes. And from that point on, the users of the network, not only the one who deploy the network, but everyone who can access to the hardware, the physical device that is emulating the QKD node, can request keys using the standardized API. And how the request go is a node get a request, so then it pulls a message to the broker, so the simulator engine, the backend, get that message, and then the Qdito simulator perform that message, and simulation results in two different things: one, the key, and the other one, the simulated time. So the simulated time is the time that a quantum hardware which have spent doing producing that cryptographic material. So then it waits for that time and then publish the key so that the node can retrieve it and send it to the client. So at the end, the network user, what is seeing is that he requests a key to a device, and then at realistic time, it gets back that key. And we have done a lot of things using this platform. So the cool thing about Qdito is that you can explore both worlds, like theoretic world and more like networking world. So we have built on top of Qdito's emulated networks, we have built different architectures. We have been virtualized key management planes, control planes, and try to play with those things to see mechanisms, interfaces, and so on. Then also the two implementations I was talking about of BB84. One of them is the one you can see in the middle column, and these implementations allow you to put any eavesdropper you like in any link you like. So that allow us to play with things like monitoring routing mechanisms, so you can avoid certain paths if you detect that something is wrong with them. And then the other implementation we give by default is more like a more complex, theoretically speaking, BB84 that allows you to touch a lot of different parameters, and it has also privacy amplification, information reconciliation, and takes into account all of this, so you can really see how parameters affect in certain protocols. And also, Qdito is not something we are throwing away. We are doing a lot of things also with it, and we plan to do a lot of things with it. First of all, we are building a testbed where we use these emulated QKD nodes that are able to speak with other hardware, because at the end they follow the same API. And we are building a testbed with 3 different domains. In one of them we have PQC, in other of them we have physical QKD commercial nodes, and then we put Qdito in the middle to act like a bridge for them, and we are able to exchange key from one point to another without any issue. And we are using this testbed for things like different mechanisms for authentication, like using physical and canonical functions. We are also connecting different points of Spain with this testbed. Also, other things we're doing with Qdito is exploring the merging with SDN controllers like the Teraflow SDN controller. And we are also using Qudito in different quantum secure communication initiatives of the European projects like the QIRG Act. So now the other big thing we're planning with Qudito is to moving it from only doing QKD related networks to be able to emulate general entanglement networks. So again, what and why? What the same platform Qudito, but this time allows you to put quantum memories and sources of entanglement pairs and so on, so you can emulate quantum internet without having the access to the hardware. Why? Because in the case of the QKD, I was saying that the commercial hardware was black boxes and it was quite expensive. But in the case of quantum internet, it barely exists. You cannot yet buy things like entanglement generators and so on and plug and play with them. So what Qudito will allow is to explore quantum internet things before building the quantum internet physically. So it will allow both things like Qudito does, more theoretical things, hardware-based, like implementations and characteristics of hardware, and then also things like what interfaces we need, what mechanisms, protocols, etc. So we would like something as easy as Qudito is today. You have your classical infrastructure, and then you tell the orchestrator what you want to deploy, and it deploys for you, and everything works fine. But obviously, we have some new challenge here. First of all, there is no standard yet for it, so we don't know yet how we are going to talk to these quantum devices. So we have not as easy as in the QKD case. Also, hardware is much more heterogeneous, so we should have a way to let people try the hardware they want and deploy it in the emulated network. And finally, Diego is going to be talking to you about service unit in some minutes, but basically service unit and QKD are a string of bits that are the key at the end, and they are classical bits. But service unit in entanglement networks at the end is the resource you use, and that's it, quantum state, quantum entangled state, and they cohere with time. So our emulated network should be able to take this into account and show the user a realistic environment. So our first approach to solve this issue is, first of all, we don't have an API, so we should be able to let the user develop any API they want. So our approach on this is to define a set of basic primitives, maybe taking into inspiration into of sound proposal like Quasm, NetQuasm, and so on. So the user can build any API they want. Then, what about the hardware? So following the flexibility we had right now in Qudito, we were thinking about setting the simulation core. Obviously, we are gonna give the user some default things like some default memory model, but if you want to use any other, you should be able to implement it and then have your own library of hardware and name maybe memory 1. I want to be deployed in node 1 and node 2. Memory 3 that is more complex and works better, I want to be deployed in node 3 and node 4. And the orchestrator should be able to read that, understand that, and deploy it for you. And about the decoherence, we need mechanisms that allows it to be on real time. So what we're thinking is you simulate when the user tells you I want a pair between this node and this node, you simulate the exchange of that pair. So you simulate the fiber, the contact channel, and so on, and you save those states at the end and save the state that they are in at the end of the exchange. And then when the user gives you another instruction, you set a timer there, And then when the user gave you another instruction, you run a simulation between the time that you save those state and the actual time. So you decohere the state, and then you perform the instruction. So to conclude, this is our idea, and we are working on it. This is the design we have. So our next first steps are first to describe those primitives, to select those one. Mainly the two more fundamental ones are create an entangled pair width and swap these two to elongate that entanglement. And then, as I was saying, we have to implement that simulation models that allow us to simulate the exchange. Then forget about the physical fiber, because at the end, if you have entanglement, you have now what they call virtual connection. You don't need that fiber now, so you only have to simulate the memory, the quantum memory, and the time spent in that quantum memory. And then the first things that comes to our mind when we want to explore when we have this platform are things like the identification problem. How do you tag qubits in a memory? So you can say, I want to perform this gate in this exact qubit, not in another one. The routing problem is better for me to go through a longer path, although it may affect fidelity, or to wait that my path is free, so the nodes in between can give me my resources to swap all the entanglement. And other things like signaling protocols, resource allocating mechanisms, control mechanisms, and so on, that we will be able to build these things on top of Qudito emulated networks. Those are questions I can not answer yet, but hopefully I can answer some other questions. Thank you all for listening to me, and thanks especially to my team that is now in the screen.
Great, thank you for the talk. We have actually plenty of time for questions, so please raise your hand digitally if you do want to ask a question. While we're waiting, I will start then. I'll raise my hand. Question from you, which is, you mentioned some handling of latency in the simulator, but how do you handle latency in the simulator compared to the real-time messaging between the nodes?
I come thinking that someone will ask this question. So basically, right now, Qudito only has problem is the key is really short. So because the hardware will be faster than our simulator, but as long as you start requesting key for more than 100 bits or so, Qudito works fine. And the other thing, also, usually the links are long, so I mean you are not emulating point to point like 5 meters separation. So if the links are long, the keys need more time, so our simulator is faster. Also, the case in the entanglement network platform, we are working on that, because obviously if we simulate the exchange and the user asks for an instruction really fast, then I think the time that our simulator will last simulating the decoherence in that time will be longer than the actual thing. But then we will have to look if it's important to simulate that decoherence, because maybe if it's like 0.001 millisecond between the exchange and the instruction, then maybe you could use just the quantum state and not simulate that, so you will reduce that latency.
Okay, thank you. Any other questions? Going once, going twice. Okay, thank you very much for your talk, and thank you for staying on time. I'd like to then invite Zian to share his slides. Not by raising your hand, you need to click share slides. Yeah, there we go. Let me Okay, Zian, the floor is yours. You have 20 minutes.
Great.
Sorry,
guys.
your sound is
I'm
really
Sia.
bad.
I'm
It's like a
currently,
robot. Can you can you adjust your mic? Can you say something now?
Oh, really?
We cannot hear you right now.
Can you hear me?
Yeah, it sounds like a robot. It's very distorted.
Can you guys hear me this time? Really? All right.
Yeah, but
Is
it's still
the
very
time getting
distorted.
better?
Do you have a headset, maybe?
Just a second.
The video quality is actually pretty good, but somehow it seems like it's low bandwidth audio. But let's see if this headset helps.
No, it's still.
Right. Is this time better?
Diego, would you be willing to give your talk right now? Yes. Well, we're gonna ask another talk right now, and can you try and fix your microphone issues in the meantime? Thanks.
All right.
One more second.
When you tell me.
Okay, go ahead.
Okay. Hello, everyone. This is a date. This is version, if I remember well, is version 04 of a draft that we were, in which we were proposing a set of abstractions. We're calling it an architecture just for as a reference for discussing about how the network potential quantum network and integration within the internet could be achieved. And well, some news of how we are experimenting this with something that is part of the QIRG UCI program. This is why we started with talking about this. Again, let me say this: we don't want to mandate concrete protocols. We don't want to identify or to decide at this stage, because it would be essentially impossible how to do things. But at least it's about a reference framework that would allow us to evaluate in a well-aligned, in a consistent way, different proposals, etc. With something that is important as well in mind, that is the fact that we are seeking this convergence of networks between what is the quantum mechanisms and the classical ones, because the idea is that we have something that is useful in both sides. It's not only about connecting quantum computers, it's about making the result of those computations and the integration available. For that, and this is something that we're trying to do first about leveraging the experience we have gained with QKD. Is something similar to what Blanca was presenting, is that we start working with QKD and then trying to derive some ideas that are related with this based on SDN concepts and trying to align it with abstractions that are related with actual network services. And let me insist on this because we're trying to think in terms of a network, not in terms of a collection of links. That I'm not saying that it's not important, but taking into account that the current internet is not concerned whether you're using optical signals, you're using radio, you're using Wi-Fi, you're using Ethernet, we are using whatever. And it's about considering it how we can think about this list of essential network functionality like routing, like access, like accounting, or like service levels and how they are established and applied. For this, in this version, what is new from the previous one is that in the previous one, we mentioned this idea that we were trying to elaborate around service units and that we have elaborated more. And the service unit is the basic element that we believe could be built to reason about how we build the networks and how we build the point-to-point, the end-to-end, not the end-to-end interactions over the network. The idea is that a service unit is, in general, is about identifying a shared state between whatever two application entities that are using the network, referencing which are the sharing application entities and which are the relevant parameters for those for that shared state. And mind you, it's not directionally. There is, when you have a shared state, there is no origin, there is no destination. Probably there is in the moment of establishing the route, but once you have the shared state, the state is shared, that's it. Somehow there is an analogy, thinking about this is something that is an analogy to how I identify transfer flows between two entities. The famous, those of you that, I guess that most of you have used to the 5-tuple. These are the IP addresses, the 2 ports, plus the protocol. Here we're talking about the two entities, plus the parameters that are relevant for this. Totally abstracted, and this is something that the idea, because we're talking about a network view, abstracted for specific link or repeating strategies, and ideally being able to be used with different links and repeating strategies, and in support of, well, the 3 essential properties that, well, in the draft are mentioned about agility, so the mechanisms for using and reasoning about the network can become independent on how technology evolves, sustainability, so we are able to build an internet in the sense that we have disjoint segments in terms of management, in terms of technology, etc., but can be integrated, and pliability, so we can converge. We are not required to invent a new set of operational practices, and we can apply, well, or at least make evolve in a reasonable way how things are going to have to evolve in the future for the quantum-enabled internet using the same mechanisms we are using now. We have made, in the draft, there is a proposal that by identifying the service units using 3 URNs. One per entity, one identifying the entity and some parameters within the entity and the applicable parameters. Why URNs? Because URNs have a set of properties that make them useful. Discussing with some colleagues, they say, no, we can use simply an IP address. Well, the IP address can be inside the URN, but you can use other mechanisms that allow you to identify the entity and identify the parameters. Up? No. Yes. No. Here. Back. So, with this, when talking about addressing network functionality, we have the possibility of aggregating and delegating pieces of the URN the same way that you do with an IP address, but it's a little bit or much more richer. That depends on how you look at it. And that support, which is quite interesting, exactly the same global and locally restricted addressing. So you can choose that you have only local addresses that are not going to expose, things that are going to be shared, global addresses that are going for the whole network. And, well, that's what we use right now for routing, and that hopefully, I mean, in the foreseeable future is what we're using for deciding which is the route and finding the other entity to be connected with, is something that supports access and admission control, that implies authorization policies, that implies for the entities and the parameters, and that the idea that we put the desired parameters for the shared state there is something that support to include the network state and have admission control as well. For sure accounting, we're identifying the entities. It allows us to trace who wanted what, who was connected to whom, from and with which characteristics, and make this the traceability of these decisions. And service levels, because we are incorporating in the definition of the service units anything that has to do with the parameters. Well, in QKD, and we are experimenting with this right now, and well, this diagram is very similar to the one that was used to present Kudito, but it's part of the experimentation we are doing with this idea that we have service units that are bit strings. I mean, once you have the QKD protocol, at the end you end up with a string of bits that can be used as a key. And the idea is that each application entity identifies itself to the key management entity that is the one in charge of providing the keys, and and they are built, and they're from the same that we have a port, we are advocating to use anons to identify independently per each application entity the particular instance. And whatever the management entity, the KMS, the domain in which the coordination is taking place, decides about how they are managed, with the URLs that are global, domain-wide, local, and the curious thing with our, well, the curious, interesting property we were looking for is that you can apply any kind of routing strategy, and we are playing with the idea of using SDN controllers or using mechanisms for route reflectors. If we generalize this, well, or when trying to generalize this, is that thinking about a shared state that is going to be consumed by the application entities. In general, right now, what we can think is that we're talking about addresses in quantum memories. You have at the end quantum memories storing entangled states, and the idea is that what you have as a service unit is an address or a set of addresses in those quantum memories for those shared states that are going to be consumed by the application entities by whatever the means. Though, as in the QKD case, there could be some specialized contents. If you think about sensing, or you think about teleportation application using a sort of network coding, you can think about, the previous or the coming talk that is going to be about positioning, etc. You can think about specialized service units once they are purified, refined, processed by classical links, whatever. That's something that is suitable to be, I believe, it's suitable to be applied, and using a very similar interface based on these application entity identifiers that are assigned, the same that they are assigned by the KME. In the case of QKD, those are assigned by the service stratum of the 3 stratums that we have in the proposed architecture. And everything goes in a similar way, right? We believe that this can be extended, and the plan is to make some experiments to demonstrate the possibility. This, if we go to the architecture, if you remember the architecture, well, those of you who have looked at the draft or where in previous presentations, we are talking about 3 strata, one with a service, one for the quantum forwarding and the quantum protocols, one for the pure connectivity to build the network and the physical network itself. And the idea is that in each one we have a control plane, and for sure the interaction with the application happens at the service stratum. The control plane of the service stratum will make requests. We'll receive the request from the application entities, and we will interact with the quantum forwarding stratum and the connectivity stratum to derive and to start to establish service units between the 2 applications. And which is important because we have a telemetry plane in each one, is that monitoring can be activated. We know how to activate telemetry at the connectivity stratum. We can imagine easily how to activate telemetry at the service stratum. And well, we had to start thinking about how to activate some kind of telemetry at the quantum forwarding, and this is something that as well would need some research. And with this, I think I have finished. Well, no, this is about what we are doing here when they're experimenting. This gentleman in blue there is the one who is author of this, and he knows much better than me about this. But well, basically, this is the network we are experimenting with, which is very much focused on QKD right now. That has more than 400 kilometers, more than 40 QKD modules. We are using Qdito for experimenting at scale. We were experimenting with token-based application access control as well. So we are trying to integrate the whole thing and the whole ideas we have. I know I have less than 2 minutes. And we are trying to, on the one hand, moving beyond quantum QKD, not necessarily a generalized entanglement. We are trying to experiment with other mechanisms like load balancing, positioning, etc. And well, this is just to give you an example. This small circle there with our logo, with the Telefonica logo, we are trying to apply the principles. You have the 3 planes that we propose for QKD and how they translate into the logical level, but the SDN level, so to say, and then what you have is how this looks physically once you integrate all switches, all the mechanisms, etc. So it's becoming complex, but it's something that we are somehow used to, but it's how we move, just to illustrate how we move from the conceptual level into the real network and the real physical, practical deployment. And that's all. I more or less did it in time.
Just about. Very rapid question, Rodney, if you have one.
Yeah, I think we lost another person in there. Now I've forgotten what I was going to ask.
No, there wasn't.
So the generalized service units that you're talking about there, are they usable for applications that are building entanglement? I didn't quite grasp that.
In principle, yes, because what we have in mind for that, Rod, is simply is a set of addresses in the different quantum memories. The same way that you have in QKD. I mean, how they would look in the future would depend on how we address the quantum memories and how we identify the addresses. And this is something that we are trying to look, because at the end, when addressing a quantum memory, we need to identify the states. It's something that we have been, I mean, is it the usual problem of how you point to an individual qubit for a particular computation or a set of individual qubits? It's the same problem. Once we have this solved or this is clear, that should be what is inside the service unit.
All right, I think Wojtek's going to cut us off here. Paventa, I'm sorry, I would like to let you have that question.
Thanks, Fred. Is your question fit?
Sorry.
Go ahead, yeah. Let's just do your question and then... Oh, no, do you want to ask a question if it's quick? Sorry.
Hello. Thank you so much for the presentation. I'm Poonam from University of York, UK. So my question is, because you're working on SDN, what is the complexity you're thinking about in terms of the hardware architecture?
Of the SDN?
Yeah, your whole architecture you are presenting.
In terms of hardware?
Yeah.
In terms of hardware, right now what we have for this kind of what we are running, well, we are trying to mimic the same or a similar architecture that we have for the optical network, and with each one of these domains there is a controller, and they are integrated with a higher level controller that knows about the whole network states. I would say, I mean, with replication and all the like, in terms of the controller, probably we are talking about, I don't know, Antonio, 16, 20 nodes? I mean, 16, 20 rackable PC servers, nothing extremely complex.
Okay, sure, thank you.
Great, thanks again, Diego. Zian, do you want to come online now and show your slides? Can you say something?
Yep.
Okay, it's much better.
This time?
You're going to have 3 minutes less, but go ahead. The floor is yours.
Okay, great. All right. Good morning, everyone. I'm Zian. I'm currently a PhD candidate at the University of Amsterdam. And today I would like to bring the topic about the quantum position verification, which is a feasible and exciting application in quantum networks. And this work has been published in InfoComm this year. So to start with, I would like to introduce about the very basic, the classical position verification, which uses one's location as a token of identity without requiring a pre-shared crypto key. A very simple example can be given as the bank and the authorized position. So a person at this position would like to request a transaction of money from the bank. And then the bank verifies this person with its location and a puzzle. if the authorized guy if the person at the other end can reply in time, and then the bank would accept and approve this transaction. So the very basic protocol of this position verification is called the distance bounding. It measures and limits the maximum physical distance between two communication parties, just as the figure I showed up here. So you can see that actually the distance between Alice and Bob is bounded by the speed of light and the round travel time between the Alice and Bob. So everything, if this distance is less than this, and then I would prove this location as saying it is accepted. But there comes a lot of questions regarding this classical distance bounding because we're using classical message and everything is bounded by the round travel time between the two parties. So if there is an attacker sits in between and intercept the message and calls back to Alice before the message arrives at Bob, then it could be a very perfect attack because it also falls into this time-bounded constraint. So there are two main drawbacks regarding this basic protocol. First, it's very easy to attack. And the other thing is that it only gives the upper bound of distance. So here we introduce quantum into this position verification protocol. But why quantum? The first is that the qubit carries much more information rather than the classical bits. And the other reason is that the measurement outcome of the qubit depends on the measurement basis. Also, we introduced that entanglement, this unique and strong properties, which is a very strong relationship between two particles. So the measurement of one particle and is linked to the others. Just as the figure showed up here, if like on the Bob, it matches with this EPR pair and matches in the measurement basis. It could be either 0 or 1, and in the other basis, it could be either a plus or a minus. So here I give a definition of the QPV commitment protocol. To start with, we need 2 verifiers and a prover. And we also need 1 entangled qubit pair. And also that the key is to determine the measurement basis. At time 0, the verifier V0 sends half of this pair, which is the qubit Q, to the prover. And after a short time gap, both verifiers send the keys X and Y to the prover. After the prover receives the qubit, and the prover sends a commitment to each verifier to indicate it receives the qubit or not. And then the prover measures this qubit Q based on the measurement basis that he received from both two verifiers. And after the measurement, the prover sends the outcome to each verifier respectively. And then each verifier checks the result and the total elapsed time, because this protocol is still bounded by the speed of light. So if our results match, then accept the position. Otherwise, they mark this round of running as fail. So here comes to the research question that you can see, like in most discussions, especially the theoretical papers, they are all limited to one-dimensional case, which is the protocol that I just showed to you. So how can the protocol's reliability be assured in the higher dimensional settings, like in real life? Also, how should the verifiers be positioned in higher dimensions because they have much more places to be placed rather than a line in the 1D case. Also, people often overlook the practical constraints in talking about this protocol. So what constraints does this protocol face in real-world settings, and how could these constraints be assessed and mitigated? So our work answers these 4 questions. So the first step, we propose the QPV protocol in the higher dimension. In general, we have to have, like, in the n-dimensional QPV task, we need at least n+1 verifiers. So here the figure on the right hand shows a topology for a 2D QPV case, which means we need 3 verifiers that covers the prover at the middle. Also, we assess the constraints using the quantum network simulator. In this case, we use the topology from the quantum Delta Netherlands plan, which is a national project for the quantum network deployment. And we also use the NetSquid as our network simulator. We use the setups from the experimental data. Then there are three key practical constraints regarding running the QPV protocol in real life. The first is the photon loss, and the other is the quantum operation error. The third is the clock synchronization. So regarding the photon loss, because of the no cloning theory, you cannot simply send a identical copy of the qubit to the other end if this has failed. So additionally, that the photon loss will cause the information loss in regarding the transmission of the qubit and the classical keys. So we can see here we do the simulation and we show the relationship between the distance and the protocol's error rate. We can see actually the black line denotes the photon loss. The photon loss dominates all the constraints that are around this protocol. The other is the quantum operation errors, which I think is very familiar with you guys. Basically, that's only the spam error is the main property regarding the constraints in running this protocol. It can be divided into two parts: the state preparation error, which happens when you are trying to prepare a quantum state. The other is the measurement error, which is the error that determining the current quantum states. So we separate these two errors using the simulation because, like in experiments, it's very hard to split these two errors. We can see that the black line denotes the measurement error and the blue line denotes the state preparation error. Also, from this simulation, we can see that the measurement error actually denotes the actually leads the main error regarding the quantum operation errors. The third constraint is the clock synchronization, because our protocol that we want to make sure that all messages arrives at the prover simultaneously, and that means that we need to have a very higher acknowledgement of all the messages, even the qubits in the channel. So any failure to synchronize arrival times could allow an attacker to exploit this time gap and compromise the protocol. A possible solution is to use the control plan, which we can actually have the flexibility and a very precise knowledge of all the messages we are sending and we are scheduling in the network. So let's go back to the topology, and we can see like from each verifier to the prover, there is a region that's caused by the allowed time window, and the region can be expressed as the equation shown up here. So this is the region formed by the maximum allowed route travel time and multiplied by the speed of light. However, we can see there are like several overlaps in this ship. So basically, there are two types of it. The one is in the pink triangle, which is the 2/3 of the overlap. The other is the 3/3 of the overlap. So it actually means the chance that the attacker can intercept the message. 2/3 means that the attacker can intercept 2/3 of the messages from the verifier. And orange, which is the 3/3 region, which means that the attacker can intercept all of the messages we sent to the prover. Also, the prover has to be stayed inside this 3 out of 3 interceptor region to make sure that it can complete the protocol. So thereby that we define this orange interceptor region, we call it danger zone, which means that within this area, a malicious prover can make the verifiers accept. So here we think about and analyze this danger zone. In the best case, the danger zone is shrinked as a single point, which is the exact place of the prover. That means that no one can intercept the message and no one can break the protocol. But if we think about the maximum, think about like in an infinite space, this region expands and expands, and then it comes to a circle. So this maximum circle is actually depends on the distance between between each verifiers. And in the worst case, so the radius, this is given by the 33% of the distance between the verifiers. So what about things in between? We put it in the space-time to analyze what exactly danger zone could be in the in any setup of the networks. So in the theorem 2 that we given that the danger zone, a definition of the danger zone. Then we'd like to implement this QPV protocol in reality. So we have to think about the process regarding how should we run this protocol. So we separate it into 4 steps, which is the select the nodes, concerned about security, execute the protocol, and then we verify the location. And we first propose a verifiable vertices selection algorithm, which can takes 4 input parameters, the network topology, 3 verifies location, and it gives back a set of verifiable nodes within the graph. So this algorithm identifies the nodes which can validate their location with our designated verifiers. Then we leverage our danger zone theory. We then proposed a malicious prover location identification algorithm. It takes more parameters, which is 6. It takes the network topology, the prover, and 3 verifies the location. Also, we have the estimated prover's responsible time. Then it gives us back with a set of potential malicious provers in the current setup and in the current network topology. So here that we show the case study based on the QDNL project topology. In the first case, we choose Amsterdam, Den Haag, and the Wallery as the verifiers. And then we can see all the green nodes could be set up as the prover. And then in the second case, we still use these 3 cities as the verifiers, and we would like to verify a guy in Eindhoven. And then the MPLL algorithm and gives back a circle that which is the danger zone that we proposed. It includes that all the malicious all the possible positions of malicious prover. And luckily, in this current setup, we could see like no other nodes are located within this area, which means that this round of QPV protocol setup is 100% safe. Also, we would like to study the workflow of this protocol because, as we said before, that we need to have a very precise acknowledgement of all the messages that within the that's happening while running the protocol. That means that we need a control plan, a controller, to schedule all of these processes, and we communicate with the southbound interface and to let the controller initiate the node selection and all these 2 algorithms, and then we let the controller to collect and compare the results it gets from these verifiers in the network. So here comes to the conclusion part. We identified 3 primary experimental constraints for this protocol, and also precisely defines the danger zone regarding the protocol security. We also introduced these 2 algorithms and VVS and MPLI based on our findings to enhance the protocol's visibility. So in the future, I would like to explore even in higher dimensions, like in the 3D case attack models, and we would also perform a numerical analysis to evaluate the performance. Also, we are assess the impact of how should we design the control plan regarding this protocol efficiency, and then would also like to validate the methodology on an experimental testbed. We're working closely with SURF and TU Eindhoven and CWI all in Netherlands. And thank you. And here comes to the question part.
Great, thank you for your talk. Time for one quick question before we wrap this up. Anybody have a question? Sorry, the queue was locked, so if somebody tried, please do it again. No questions? Yeah, just go ahead then, Diego.
This is Diego. Just they don't have the time for raising my hand in the. We are almost over time. Now, it's about the MBI you have mentioned for the controller. What is this based on? I would say is a typical SDN MBI, the northbound interface of the controller, or you're using REST interface. What is the kind of interface you're using there?
Thank you for your question, but you can see this is just like in a workflow that we just proposed. We haven't decided like which exactly interface that we would like to adopt. So we would like to investigate in the future studies.
Okay. No, I was thinking about this, and this is what you're talking about, the control, the influence of the network control is about how the controller translates the MBI requests, or how the controller is about, keeping somehow the states of the quantum nodes in a particular, I don't know, it's just asking what you have in mind when talking about the control effects.
I'm sorry, can you expand a little bit?
You mentioned that one of the open issues is about the effects of the network control in the measurement protocol, and when you talk about these effects, I would like to know more about which are those effects that you envisage.
Yeah, we would like to talk more about the time synchronization, like based on the control plan. So we would like to use the control plan to synchronize the message and the qubit arrival times. But actually, it's very difficult to achieve in experiments. So, but the thing is that even like a minor unsync rate that would cause the like a higher chance of the expose this protocol to the external attackers, and that is the part that we would like to analyze.
Okay. No. Well, I got your
Diego.
Talking.
Yeah. Thanks, Diego. I think we're now 2 minutes over time here.
Yeah. Thanks, Rod. Thanks, Zian, again for your talk. And with that, actually, this is it. Thank you, everybody, for attending. Thank you, all the presenters, for presenting, and hope to see you next time. And please join the mailing list if you haven't yet, and continue discussions over there.
Yes, there was some interesting conversation on the chat here about how to follow up with Diego and Angela. So hopefully we can do that on the mailing list, and maybe in person in Montreal. See you all in Montreal. I definitely plan to be there in person.
Yeah. Okay. Thanks, everybody. Bye.
Bye.
Yeah. Have a great week in Madrid. Wish I was there. It's a lot more fun than doing end of semester grading. I'll tell you that. Bye, y'all. Wojtek, thanks.
Oh, you're welcome. And thanks for being here, Rod.
Yep. I actually signed up as remote for the whole week, so I'm probably going to slip. I have ambitions to participate in some other meetings, but that'll have to fit in around the other university duties too. So
cool. Enjoy.
Shota Nakitor there. Bye, y'all.